What I wanted to do today is to go back to the very first session where we had that small experiment with the advanced function. Hey, Parsa, come in. Hey, we had that problem with the advanced function that we said we have a function advance which is supposed to move that first argument, the iterator passed as a first argument, by a number of steps in either direction. And we found out that in case of a random access iterator, that advanced function can be implemented with O1 or constant complexity. While for all other iterators, we have to implement it with a loop because they don't support, those iterators don't support doing n steps at a time. You have to do one step at a time. And the solution we tried to implement was based on a technique which we called tag dispatching. And the essence of the tag dispatching was that instead of solving it with one function, we solved it by dispatching the main myAdvanced function to one of the alternatives of another function which takes an additional argument, and that additional argument type is distinct for the two alternatives. For simplicity, we just said one function will be chosen when the third argument is of type false type, and the other alternative will be chosen when the third argument type is of type true type. Which allows us to decide at compile time which of the two alternatives to choose and to actually compile into the code. And the reason we have to do that at compile time is that if we made that decision at runtime, then essentially we had if this random access iterator do this, otherwise do that. But that means that the compiler has to compile both functions, which will give us a compilation error at this point, because if the iterator is not a random access iterator, but a forward iterator only, then this operation wouldn't be defined and we would get a compilation error. So we have to make that decision at compile time. We have to make sure that the compiler looks only at the function we are interested in. Namely, if it's a random access iterator, this function is compiled and that one is ignored. And if it's not a random access iterator, this function is compiled and that one is completely ignored. And that's the trick here. So we want to make sure that the code which is invalid isn't even considered by the compiler at compilation time, which avoids compilation errors, right?
So if you had two instances, one that used a random access iterator and one that didn't, the code would compile both pieces of code and apply them in the appropriate
right. And you would get two versions of the advanced function, one for the random access iterator, one for the other one. And you would get two completely distinct code paths which are independent of each other. And both would give you the optimal result, because what we are after is that optimization which gives us that constant effort compared to the linear effort we had to invest in moving the iterator forward. And that's a point where we stopped because we didn't know how to do that. How to generate that third argument in a way that it is false type if it's not a random access iterator, and it's true type if it's a random access iterator. And all we just did it manually. We just switched that for true type, false type, and passed one or the other, and we saw that the compilation actually succeeds. And I stepped through the code and I showed you if that is false type, that one will be chosen, and if that is true type, then the other alternative is chosen. I hope you remember that kind of vaguely. It's kind of months back. That's why I'm reminding you a bit more extensively. And the solution I sketched was that we probably need some facility which we call is random access iterator, which is a template which is instantiated with the iterator used as the argument to that function. And this thing is supposed to evaluate either to false type or to true type, depending on whether that thing is a random access iterator or not. And since we didn't know how to do that, we stopped at that point and we started to talk about templates and template types. But now you can already guess that we should be able to implement that easily, because we talked last time about meta functions and about type traits and how to introspect a type and extract certain information from a type. And what I want to do today is to implement that is random access iterator type trait for one, and show you that things really work the way we want. And once that's done, I want to start with what I promised to do last time. I want to start talking about SFINAE as another technique, which is very important in C++, at least to understand what that language feature does, because it helps us to solve this in a completely different way, and I show you that you can do it differently as well. Okay, so let's start. What do we have to do in order to figure out whether a thing is a random access iterator? How would you do that? How do we know that something is a random access iterator, a type? If I give you a type, an arbitrary type, how can you know that it's a random access iterator? Anybody?
By tag?
Huh?
By tag?
Yes. You have to know that each iterator type or each iterator defined in the standard library has an associated category. If it's a random access iterator, it has an associated category which is called random access iterator tag. If it's an input iterator, it has an associated category of input iterator tag. So the standard library already has some facilities which allow us to identify iterator types. Please note, we are not looking for a particular iterator here. We are looking for a category. We are looking for all random access iterators, even for those random access iterators, the writer of this code never has heard about. So we have to have a means of looking forward and identifying things. And as it turns out, it's fairly easy to do. So let's try to do that. I'll go up here. So the first thing, as I said, let's write that down. A random access iterator. Random access iterators have standard random access iterator tag associated with them. Random access. Is it this way? Yeah, I think. Right. And this is a definition of that tag in the standard library. Right. So there is a type which the standard library defines for us, which is called random access iterator tag. And what we need to do, we need to write our meta function, which probably takes one argument, and which we call is random access iterator, and which should either evaluate to true or to false. Now you probably remember, what do you do if you have an if-else problem in template metaprogramming? Everybody remembers that? What do? You create a specialization, template specialization. You have one template which evaluates to true and a specialization which evaluates to false, and then you make the decision which of the two to choose, right? So let's do that. And hold on, how can we do that? Well, we developed that if thing last time, right? You told us to develop a meta template which evaluates either to true or to false depending on, well, to one of the two types. Let me reproduce that for you. That might be an easy solution for this case. Where is that? I should have it here somewhere. Factorial and remove recursive. If, here we go. Here's what we had last time. So what that is, so we say our random access iterator is true type and standard false type. And what's missing still is the condition. So if this is true, then random access iterator will evaluate to true type, and if that condition is false, that whole thing will evaluate to false type. So that's what we want. Do you remember that if thing, or do I need to explain that again? If was taking a flag, and if the flag was true, then it evaluates to T1, and if it's false, then it evaluates to T2, the whole thing. So that means if this is true, it evaluates to true type, and if that is false, it evaluates to false type. What we need is that condition. So how do we get that condition? What does it mean for an iterator to be a random access iterator? Well, we already said all random access iterators have a random access iterator tag associated. So what we need to find out is how to figure out which tag is associated with which iterator. And luckily, the standard library gives us a means to do that. Because what the standard library does, it defines a so-called iterator traits class. It's a template type which is specialized for a particular iterator and which has an embedded type def which is called category. And that category is the associated category of the iterator. So let's see how to write that. Let me sketch it first. So we have standard iterator traits iterator category is what represents the category of this iterator. So if this iterator is a random access iterator, then the whole thing will evaluate to random access iterator tag. If this whole thing is not a random access iterator, it will evaluate to something else. So what we need to do, we need to compare the type, this whole type, to standard random access iterator tag. Standard random access iterator tag. So these two things have to be equal. So that first thing should evaluate to the same type as that other thing, and then iterator is a random access iterator. Next question, how do we compare types when the two types are equal? Have we talked about that? I don't think so. We haven't wrote a template meta function which allows us to tell whether two types are equal. Let's write one. Template, type name T1, type name T2, struct is equal. And again, we have a decision to make. So what we need is specialization. Let's assume that one is false. And the specialization, how do we write that specialization?
T1, T1.
Or TT. Okay. So we created a meta function which allows us to tell whether these two types are equal. So if they are equal, then the whole damn thing evaluates to true type. Otherwise, it will be false type if those two types are not equal. But again, we use the pattern matching capabilities of the template instantiation mechanism in the compiler to figure out whether two types are equal, just by saying, hey, these two types have to be the same. I don't care which of those, can be any type, as long as they are the same. Please choose this specialization. Otherwise, choose that specialization. And that gives us a means of comparing two types, which would be this, is equal one type two types. So this thing evaluates to true type if these two things are equal, and evaluates false type if these two things are different. Everybody with me? If you remember, we also said that the convention is that a meta function exposes two things: a embedded type called type, which is a type result of the type calculation, and an embedded value, which represents the Boolean value of that trait. And if you remember, well, you know, the if requires a value, right? A bool. We wrote it that way. If required a Boolean value. So we have to access the colon value of that equal thing. So let me copy that. And you will see that we can even simplify things a lot in a second. Colon value. Let me just indent that a bit more so that you see what's going on. If, yeah. So this is the first argument to if. That's the second, and that's the third one. So the first argument is the comparison whether these two things are equal. If these two things are equal, the value will be true, and if these two things are false, not equal, then this will be false, which will select the proper alternative for the if clause. And that should do the trick. This, I don't like that squiggly line there. Let's see what's going on there. I might just misremember things. It's called iterator category, not category. And at this point, you see that actually we don't need the if, because the is equal already gives us what we want. Right? The is equal is already either that one or that one, so we can get, it's kind of double magic we are doing here, which is not really necessary. So we can get rid of the if and that true type false type, because the is equal already gives us what we need. So the final solution to that thing is this. Is equal okay. So and now let's read that with human words. We have a meta function is random access iterator, which takes one argument, and that random access iterator will be true whenever the iterator category of that iterator will be random access iterator, because these two things are equal types. Otherwise, it will be false. And that's it. And isn't that what we wanted? That's what we wanted. So let's try that out in our code. All what we need to do now is to, instead of and remember, we have to put a type name in front of it. And that's it. So what we, okay, I mistyped it. Random, I think I had a space here, I didn't underline here. So that's our tag, our meta function we just wrote. We pass our iterator to that meta function, and the embedded type of that meta function. Let's go here. That thing will have an embedded type which is called type. Why? Because it's derived from is equal, and is equal has an embedded type called type. Why? Because both specializations of is equal, both have an embedded type called type, because that one has its own embedded type called type, which refers to itself, and that one has an embedded type called type, which refers to itself. So in the end, our is equal evaluates either to one thing or to the other thing. So it's exactly what we wanted. So now let's see if our code really works. My advance. And I left the palindrome function in here because we were using the advance here. And now let's invoke the palindrome function with a vector of chars. And the vector of chars, the iterator of vector of chars, is a random access iterator. So let's see if we end up in the proper space, in the proper place. Let's set a breakpoint here. Compile the thing. I hope okay. See, that's the error you're getting when you're forgetting a type name. It says standard iterator category, dependent name is not a type. This means I forgot the type name in my code. That's what we were talking about last time. When do I have to use a type name? Well, I have to use a type name whenever the compiler tells me to do so. It's the simplest answer. Now it compiles. And now let's run it and see what we've got. I step into the isPalindrome function. And now I step into the myAdvance function. And now the magic should happen, right? Because now we should jump either to the one which is written for a random access iterator, or we should jump to the one which is written for a non-random access iterator. And see, magic happens. It actually jumps to the function. You can see the arrow here. That's where it's sitting in the code. It jumps to the function which is for random access iterators. So it's exactly what we wanted to achieve. And now let's change our code to actually use a list instead of a vector. Because now we know lists don't have random access iterators. Lists have bidirectional iterators, which are not as powerful. Bidirectional iterators don't support plus equals n. We can't do our advanced operation in one step, but we have to do the use a loop. And now the code still compiles, and let's see what happens now. It's my palindrome function, my advance, and now, look, now it jumped into the other one. Selecting the proper function with a proper loop, and not instantiating the one with a plus equals n. So we achieved exactly what we wanted. We decided compile time just based on the iterator type which is provided to the function, which of the function to select and which of the functions the compiler will actually use for compilation. You might say, okay, all nice and dandy, but I have an additional argument here. Isn't that additional overhead in your code when I have to pass an additional argument to that function at runtime? Well, you might be surprised if I tell you the compiler will optimize away this argument, because it's not needed anywhere. And we didn't even give it a name, right? That argument has no name. We don't use it anywhere. It's really just there for the distinction between the two functions. So the compiler will happily optimize that thing away and will not even generate code which passes that along to the function. So it will even optimize away that higher level myAdvance function. It will not exist anymore. It will directly call the underlying function we need once all optimizations have been applied. And since I haven't optimizations enabled, we could follow what it's doing, but if we enable optimizations, these things will just go away. And that's what I meant in the very beginning when we started to talk about C++, when I said C++ is a language which gives you higher level abstractions and still full performance, because the compiler is doing all the hard work to collapse all the abstractions away for you and remove them at compile time. They will go away. Well, what we could do, we could try to generate, fully optimize it and see what happens. I'm not sure myself what will happen, but let's try it out. Let's do release mode, which enables optimizations, but still let it generate debug information so we can step through the code. So let's see, we have that done. And I think we have to enable all the optimizations because at some point I disabled that. So full optimizations. Yes. Okay. So now I step into the function. I advance. See, and the function, it will not even step into the function because it optimizes even away the advance itself. So let's try to look at the assembly code it generates. Let's see if we can discern something here. Where's the assembly? Here's the assembly. I want to use that one. See where the loop is. So if I understand the code correctly, this is our loop. This is our loop. Subtract 1 from the counter, and if it's not equal, jumping back somewhere to advance the iterator. I don't know where the iterator advancement is. But this is, here we have clearly a loop here. Yeah? Subtract 1 from the counter, and jump not equal. If it's not 0, do jump somewhere, otherwise fall through. So let's see if we switch the iterators, and then we can compare the code we get from the vector. And that will clearly look differently. We shouldn't have a loop there, right? Whatever it does, we shouldn't see a loop. So let's look at the disassembly again. And very interesting. Well, we clearly see we don't have a loop anywhere, right? We don't have a subtract 1 with a jump. At least we know that. My guess is that this add operation is the plus equals n we had in our code. So it clearly selected the other code powers and completely optimized away all what we did with that meta function. It doesn't even appear anywhere. So there's no arguments generated which are being passed to the function to select that and so on and so on. So the compiler is fairly powerful and fairly knowledgeable in looking through levels of abstractions and taking away what's not needed anymore. I don't need that. Okay, crap. That's that code. Crap, I don't need that. So it collapses all the, or a lot of the abstractions I'm building on top of itself, which gives us higher level abstractions with low level, with high level performance on very low level code. Well, I don't understand that fully because I haven't analyzed it, and you don't have to understand it. The idea is really just to show you that even the call to the advanced function is going away. We don't see that anymore. Do you believe me? Right? A call should have call written here with a function name when it calls a subroutine. So we don't even have that anymore. It's gone. Okay, so far for the tag dispatching example I wanted to show you. Any questions so far? Overwhelmed or just no questions? So for normally you have questions. No? But can you follow that? Is it understandable? Good. Okay. So I introduced a first technique to you, which is called tag dispatching. And tag dispatching is used to distinguish two or more functions based on a distinct argument type. And then you generate the proper argument type to select one of those functions at compile time, which allows us to avoid compilation errors. Because one code pass might not even compile for certain types, right? That plus minus n, plus equals n will not compile if the iterator is not random access iterator, because that operation doesn't exist, is not defined. Okay, full stop. Next thing I want to touch on is what we call SFINAE. And I think I wrote it out last time. Magic works. So SFINAE. SFINAE is one of the most strange and most misunderstood features in C++. Not even talking about the strange acronym, which stands for substitution failure. Substitution failure is not an error. Okay? And you might say, hey, why do we need SFINAE? Or why do we need something like SFINAE in the first place? SFINAE is a feature of C++ which is built into the language, and is built into the language from the very beginning when they introduced templates. And it means the following. If I, as a compiler, have two or more alternatives to select a function in a particular context, like that myAdvance, right, where I have two possible functions in the overload set, and I have to select one. Then the compiler tries which of the function fits best. And if during that trial of instantiating the templates which into a concrete function, if any of the substitutions of the template argument into a real type creates a compilation error, then this error is ignored as long as other alternatives exist. So if one of the functions doesn't compile because the type just doesn't fit into the function, that's called a substitution failure. And that one is not considered an error as long as I have other alternatives. And only if there are no alternative functions left after I tried all of them, then the compiler will generate an error. And that's very important because sometimes you get wrong code, right? Just if you provide the wrong type to a function, you get code which does not compile, even if other function overloads might still give you the right answer. So it's a very basic and very, very necessary feature in C++ when it gets to templates. Because templates can do whatever you want, and we talked about templates being duck typing essentially, right? The compiler just replaces stupidly all template arguments with the types I provide, and then tries to compile that stuff. And if it works, it's fine. If it doesn't work, you get either a compilation error or you hit SFINAE, which means that this particular thing can't be used in that particular context. Okay? That is SFINAE. So why is that useful? Well, let me do an example, just to avoid talking.
So haven't we been using that this whole time?
No, we have not. What we have been using, we have used function overload selection based on argument types.
We can see what you're typing if you want us.
Thank you. I just commented all the code we just code, so I didn't do it. Right? What we've been using is C++ allows you to have functions with the same name as long as they have different distinct argument types or distinct number of arguments.
Right.
And that's the facility we've been using. Right? The compiler sees, okay, 3 arguments. It's distinct from the third function, which has only 2 arguments, so it falls out of the overload set immediately. And then it tries to match the argument types directly to the arguments. And then it found something which directly maps my argument type, so it selected that function from the overload set as a one to be compiled. That is completely distinct from SFINAE, because SFINAE is limited to templates only, and function overload functions even for non-template functions, right? You can have a function with straight types without being a template. And Yeah, well, that's it, essentially. So we haven't been using that. We have been using the overload selection mechanism of the compiler without even generating compilation errors while selecting the overload. It just didn't match, so don't use it. Okay? So it happens even before SFINAE kicks in. That is the first pass the compiler does. Oh, do I have something which fits? If not, then it tries to instantiate templates and gets more sophisticated, and then the SFINAE selection might hit on it. Okay, so let's do a simple function which negates an integer. There's nothing more. Okay, simple enough. But we want to be more sophisticated, and we want to allow for the user to have a template function, provide an additional template which does more things while negating. But we know negation for integers is simple, so we just want to do it that way. But in the generic case, we want to have a negate function which takes one template argument, t, and I'll come back to the return type in a second. And we just assume that for any other type, the negation will be achieved by calling a special function, or calling a member function on the type, which is called negate. Okay? Let's get really wild and say I have special types which have a member function negate, which do a negation of the current thing. But for integers, I know how to do that. And I could add a function for doubles and for all kind of other types. But I have these special things which have that negate thing, and I want to use that. Well, how can we do that? To give you an example. This one does something. It just returns a new foo with, I don't know, -1. So it's a fairly contrived example. Okay, let's say that one has a member of integer data, and the data is initialized from its own construct argument. So whenever I have a foo object, I want to negate it, it will just turn into a plain -1. Let's do it that way. Okay? Or not even do it that way, but yeah, okay, let's do it that way for now. So A, we have to decide what will be the return type of negate. In the simplest case, that could be t itself, so just return the same type as I have here. In our case, that would be the case because negate returns foo itself. But let's say I want to have a case where negate returns actually something else than the type itself. For instance, Boolean or whatever. So what I need is I need to rely on the type to give me the thing it returns as an embedded type. In that case, it's foo return. Oh, let's call it return type. Okay. So essentially, what we did, we say whenever I want to negate an integer, I do this. Whenever I want to negate something else, I return a type of which is defined by the original type itself. In our case, it returns itself, I believe. So in that case, the return type is foo. So each type provides its own return type. So when I use a string, it might just return I don't know what. And if I do it with my foo, then I get something else back, and so on. And this is exactly the case where SFINAE kicks in. Because what happens in the following case? I know it's contrived and very, very, you might think it's not useful, but it's kind of the simplest example I was able to come up in short time. At least, is everybody following that or doing this something? You're not looking happy.
No, I'm trying to.
Yeah? So let me repeat again. That negate function assumes that it will return a type which is defined by t itself. This way, as I did it there. It has an embedded type def called result type, which is referred to here. And that allows us, for the negate function, to return types different from the thing I'm looking at in the first place. But it puts some constraint on the types I can use, because the types I can use have to have an embedded return type in there. So what happens if I use a double, if I call negate with a double? Let's put ourselves into the shoes of the compiler. What would you do if you were the compiler?
Give you a compilation error.
Why?
Okay.
So if I do this, I want to call negate with a double.
Oh, okay.
Okay? What does the compiler do? The compiler will first do the following. It will say, okay, I'm not an integer, so I put that aside for now. Then it goes in and puts a double here. But it figures out, hey, damn, double has no embedded type def, which is called result type. Because double : result return type doesn't exist. So the type has no embedded thing I can refer to. And that is where SFINAE kicks in. SFINAE kicks in and sees, okay, doesn't work. This type doesn't fit my function because I have that dependent type which is not available. So it throws it out. And then it goes back and say, actually I know how to convert a double to an integer. And it will do that. So I hope it will do that. Let's see if I'm right. Yeah. All it does, it gives me a warning saying conversion from double to int, possible loss of data. And it uses that original one was an int because it threw out the other one. But the other one would be the preferred one because it's a template type. And the compiler assumes, okay, it's a template, so I can generate a function the way I need it because I provide a double. So there has to be a way to generate negate function for doubles. But it doesn't work because SFINAE kicked in. The substitution failure kicked in because the dependent type doesn't exist in double. So it throws it out, goes back and says, okay, now I'm happy. I know it's not my preferred way of doing things, converting doubles silently to integers, so I at least issue a warning, but I can do it. Because a double is almost an integer, right? You just throw away the things after the decimal point and you're fine. C has defined that, legacy of C, right? In C you can just assign a double to an integer. Not everybody's happy. A compiler will not even say a hitch or something. We'll just do that. Okay. Make sense? That is where SFINAE kicks in. Where dependent types are not available. Or some substitution failure happens in the immediate evaluation context. That's what the standard says. And the immediate evaluation context is everything before the brace. So if something happens in the body, in the header of the function, it will not look into the function itself. If something goes wrong in the function itself, you get a compilation error.
So if you had something that did have a return type, but then inside the braces of that function, there was some operator call that was not
then you get a
supported,
compilation
then you
error.
get a compilation error.
So SFINAE is really just limited to the immediate evaluation context. which is evaluated while the function overload set is narrowed down. And that is everything before the body, right? It just looks at the prototype. And if that passes, then it instantiates the function, and if that fails, then you get a compilation error. Okay?
So
Yes.
if we define a struct that inherits from int, which I don't even know if it's allowed.
It's not allowed.
All right. But if we define negate to be take a parameter, something we could inherit from our negate function, not the template. So we define it to have a parameter of something we could inherit from, and we define a struct that inherits from that. Would it? But give that struct also the return type, or which would it
Well,
call?
if the base class has an embedded type def, which is public,
Uh-huh.
then the derived class has it. We relied on that, and our is equal. Right?
So
We
go- but
relied
that's what
on
I'm-
the base classes exposing our type.
Well, I'm just asking which would it go to first? Would it go to our definition of negate or the template? That's
Whatever the look, the compiler does follow. It starts somewhere
Mhm.
and tries to match each function separately. Does that fit directly, plain, without conversion? No. Back. Does that fit? It could fit.
Okay.
Right? Then it checks that,
Mhm.
narrows it further down, and if nothing is left, it starts over and tries to apply these implicit conversion rules like double to int or int to double or this kind of thing. So lookup rules in C++ are very, very tricky. You have to be very careful with that, obviously, because of templates, because you always have to have these hundreds of different possible rules in mind to get proper overload. But that is SFINAE. As I said, a very basic language feature which is absolutely necessary for the language to function properly, for the language to do what you would expect when you write code. Right? That's roughly what you would expect, actually. That's what's happening. Very basic, very nice. Why do I talk about that? Well, as with everything in C++, some bright mind came up with an idea and said, hey, can't I abuse that? Can't I do something? Can't I build a facility which forces the compiler to ignore certain function overloads which are written, which I don't want to have? For instance, have a advanced function which will be used if iterator is random access, and the other one, when it's not random access, without giving a third argument. And that is where SFINAE is useful. And I will show you in a second how that works. Because somebody came up with a way of forcing SFINAE, give you a tool with which you can use to control SFINAE yourself. And that tool is called enable if. Let me just remove that contrived example or comment it out. Okay, let's write enable if. Template, type name, enable if, no, type name T, and type name, oh, let's do it that way for simplicity for now. Struct enable if. No, actually, it's just a bool flag. And a overload for enable if true. And the true has an embedded type def, void type. That's it. What we created is a half meta function. If the argument to enable if is true, we get a true meta function, right? Because it has an embedded type def type. But if the argument is false, we don't have an embedded type def type. That means that in one case, we have a dependent name, and in the other case, we don't have a dependent name, which is exactly what SFINAE relies on, right? If the dependent name is there, everything's fine. If the dependent name is not there, it will discard that overload from the overload set. And that means we can use enable if directly to control which of the functions are being selected and which are not. So let's go back to our advanced example. whereas here are the functions. But this time, we don't want to use a third argument, but we still have to have a means of distinguishing these two things, right? But what we can do the following. We can say type name enable if is not is random access. I need that one. So I'm enabling our is random access iterator meta function. Is random access iterator value type and in the other case I write it this way. So what do we have? What did we do? We said enable if. Then we evaluate is random access iterator on the template type colon value. We know this is true or false, right? Depending on whether iterator is random access or not. So if this is true, let's assume this is true, then which overload of enable if will be chosen? That one. Okay? That one. Please note that type evaluates to void in our case. So it will choose the one which was the embedded type def. We refer to that embedded type def of enable if. Everything's fine. And the whole damn thing evaluates to void because enable if has it defined to void. That's exactly what we had before, right? Before we had void my advanced something. So this is the return type of our function. So here, that one is fine. The compiler can compile that. Now look at that one. Here we negate the condition, not random access iterator value. So if it's a random access iterator, this one will be false. So it will choose the other enable if overload, which has no embedded type def type, which means that that colon type refers to a non-existing thing, which will make SFINAE kick in. And the function disappears from the overload set as if it wasn't there from the beginning. The compiler doesn't consider it because SFINAE has told it, no, it doesn't work. And that means that our compiler will happily choose that function, and that's exactly what we need. If it's not a random access iterator, then these two conditions will be the other way around, and the compiler will choose that function. End of story. Okay? So SFINAE is really a cool thing to have because it allows you, based on an arbitrary set of conditions, to make decisions at compile time whether a function has to be considered for something or not. And you can apply SFINAE on the result value. You can apply SFINAE on one of the arguments if you want. Whatever, as long as it's in the immediate evaluated context, in the prototype of the function. Most of the time people do it on the return value because it's simple enough.
So in the simple code, if I want to describe it, this SFINAE come to look at two compare things that I want to compare and say, oh, they are not matched, none of them is correct, so choose one of them that is nearest to the correct answer?
No, that one is really just plain either or. Either it's correct or not. This function will be used when iter is a random access iterator, and this function will be used when iter is not a random access iterator. There's no third way. Right? Is there a third way? I mean, you can't be halfway pregnant, right? That doesn't work. You're either random access iterator or not. So that. Okay, that is SFINAE. And that is so useful that the enable if thing is in a standard. It's standard enable if. With one minor extension, namely that the type enable if is using is you specify it as a type name, as an argument, because not all functions return void. And type name T, but since void is so useful, the template argument is defaulted, so you don't have to specify it. But if you want to specify it, then you just put a second argument here in here, which will be used as a return type of the function if it succeeds. So that's enable it for you. And now let's see if things really compile, just whether we did everything right here, and whether the right function is being chosen. Where's my, here is my palindrome. Let me copy that down here, because of the functions not being defined otherwise. Okay, so something is wrong. Oh, my, is equal, it's missing. Is equal, it's missing. Right, I need to do the specialization properly, and I don't know this. Yeah, yep, compiled. So let's step through the code and let's see if things really do work as expected. Well, the first indication that we did everything right is that it actually compiled. Because I have two functions with exactly the same arguments. So if both functions would be in the overload set, the compiler would have complained that, hey, you're using two functions, I don't know, you don't know which of the ones you want to use. Well, let me show you, so you believe me. I'll just comment that out and put a void in front of it, and do the same thing here. And when I compile it, void advanced blah 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 function template has already been defined. Because it's the same thing, right? So the compiler doesn't know which of the two to use. So the fact that it did compile actually tells us, yeah, something has to be right. And now let's put a breakpoint here and let's execute it for a vector. And let's see if our enable if really did the right thing here. So now we, right, vector. So we end up in the function which has been enabled for random access iterator. Now let's change that to a list again. And let's run it again. Let's put it wrong. Here we go. So for a list which has bidirectional iterators, not random access iterators, that one just disappeared from the overload set. The compiler didn't consider it, and that one fits because, well, the whole expression, as complex as it looks like, is valid, so everything's okay. I'm telling you about enable if again for the reason that if you look at code in HPX, you will see enable if fairly often, because it's used to select certain constructs depending on properties of the argument types you pass to the functions. And whenever you see enable if, stop thinking about the magic. Just take it as it is written. If this condition is true, then the whole thing is valid. If this condition is false, then the whole thing doesn't exist. End of story. You don't have to understand what that actually does and that it's embedded type and all that. No, it's really just a pattern which you have to recognize, and you see, okay, standard enable if, okay, I know what it's doing. But the magic behind the scenes is SFINAE, And I really wanted to draw your attention to it because it's a very, very useful tool to use for these things. As many of the constructs we are talking about, this is especially useful for library writers. When you write your own application, you very seldom will have a need to do that yourself. Because in your application, everything is well defined. You use doubles, you use this type, you use that type, and the functions you write are always tailored towards that particular type you're using anyway. But whenever you write a library where you don't know what the user will give you, right? Right, async, HPX async. It's a function which has an arbitrary number of arbitrary argument types. So HPX doesn't know, or the code per se doesn't know anything about what types to expect. All what the code knows is the certain properties of certain types. So async, the first thing, has to be something I can invoke as a function. And all other things will be passed through to the function I passed as a first argument. So the first argument has to be handled in certain ways, or some specifics there. If it's a member function, I have to do this. If it's a normal function, I have to do that. If it's an action, I have to do some remote operation in the first place. So there is some distinction the code has to make, and the code has to essentially, each of the possibilities is encoded, has its own implementation. But what SFINAE does, it helps us to select the proper implementation in the library for the type categories that the user provides us with. So again, when you look at HPX, this is one pattern to look out for. And SFINAE can be used, or enableIf can be used in other contexts as well, and we can talk about that at some point. But this is the most common use case for SFINAE. Just put it on the return type of a function and make the function disappear. Okay? Okay, so any questions? Now you know the secret things of C++, really. SFINAE, if you know what SFINAE is, you will win every interview. Just start talking about SFINAE to the guy who's interviewing about C++, and it might be he doesn't know what it is. Okay.
So is enableIf, would you say definitely the most common use of SFINAE, or do people find sort of novel ways of using SFINAE that are not as contrived as the first example that you showed us?
Well, that example was really contrived, and I should have thought a bit more intensely before
I mean, it's very easy to see why enableIf is very powerful, but
yes.
it's
well, the contrived example, I wanted to draw the attention to that dependent type, right? T : return type. That's why it was a bit contrived. And that's exactly what enableIf does, right? You say type def enableIf blah 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 : type, and that's where it's happening. And that's all what SFINAE does, at least in ancient C++. So this works for C++ 03 for the old versions, no problem. Since then, people have recognized that SFINAE is a very, very useful tool, and C++ 11, 14, and even 17, and the newest C++ has added additional cases where SFINAE can kick in, which is called extended SFINAE. And we can talk about that. Mainly, it allows you to do not only looking at embedded types, but to evaluate whole expressions, whether the whole expression is valid or not, and if yes, then okay, and if not, then looking whether things have, you can call a function on it, or whether certain overloads are defined, or an operation is defined, A plus B, and if yes, use this one, if it's not defined, use that one, and so on and so on. So there, with extended SFINAE, you have more ways
so that allows you to look past the braces and into the...
No, everything has to happen before.
Okay.
But what you can do, and we talked about that, I believe, you can, well, what we could do is extended SFINAE, for instance, is this. Auto, and then remember that decal type thing? You have not been there, I think, right? You can write the functions the other way around, right? You can put an auto in front of it and put the return type afterwards. Well, I probably will not get it to compile. Let's do it here. Here it's more obvious. Auto and return decal type. Decal type is a means to find out the type of something. So if I write an expression, it will give me the type of the expression. So in our case, what I want to do is this. Comma operator. Comma in C++ means all expressions are evaluated, but the whole thing gets the type of the last expression, which in our case is void. It's what we want to have as a return type. But before doing that, the compiler has to evaluate plus equals n on the argument types.
So if it doesn't have a random access iterator, that first thing won't compile.
That first thing will blow,
and
the whole thing will disappear. That's extended SFINAE. So you play tricks on the return type by adding additional expressions to that decal type, which forces the compiler to fail it. It's still in the immediate evaluated context, but you have all the power of all the expressions at your hands, essentially.
That's very cool.
Yeah. So this will work only if plus equals n is available, and I think we can even do the very same thing here. But for that one it will fail, and for that one it will succeed. So there are other ways to do SFINAE, and that's called extended SFINAE, because it has been added after starting C++ 14 actually.
You have that, like, we even need concepts.
Well, it gets contrived and gets very complex, and concepts is better because it's much more readable, right? Okay. Concepts would be much nicer, because with concepts you would write just this. Safura said I should comment out everything. Well, almost. With concepts you would write it this way. Random access iterator. That's it. Oh, well, on that function, sorry, on the other one. And random access iterator is a concept. And then the compiler knows, okay, that iter has to conform to whatever that concept defines. But we don't have concepts, so I'm not going to talk about that at this point. But there are many more means of doing things in the future, even simpler ways. But that gives you extended SFINAE. Thanks for the question. That's important. Does it make sense? Okay. Then I'll ask to stop for today, because I have to prepare for that other talk.